So, you know, I posed this problem. You've got a unit cube, define it, the parameters are very straightforward, and let the cube be open at the top, okay? And we're going to verify Stokes' theorem for this function. Okay, we're going to try to, okay? I don't think that's going to lead to a particularly nasty set of integrals, but maybe, we'll see. Okay? Now, first of all, you know, we just had an introduction to both Stokes' theorem and divergence theorem last time. And I anticipated that we might have a little trouble even remembering exactly what Stokes' theorem says. So the response I got, first response I got, I didn't give anybody time for a second one because I liked the first one, okay, is that, well, it relates a volume integral to a line integral, okay? Well, that's the right idea, okay? So let's be sure we understand why that's not quite correct, okay? Okay. So, a little side comment. We can relate a line integral I left a G out there somewhere, to the surface integral or a surface integral to a volume integral. And we know, for example, from Green's theorem, that in 2 dimensions, we can relate the line integral to an integral over the area, over the region, right? So that's a line integral to a surface integral, to a 2-dimensional. We go 1-dimensional to 2-dimensional, or we can relate a 2-dimensional to a 3-dimensional. Okay? If you think, just an analogy, and there's some parallels, but I'm not even going to attempt to draw them out because I'd have to think. But there's an analogy between what you do when you integrate. Obviously, the obvious analog is the integral of a function is the change in its antiderivative. A definite integral of a function is the change in the value of its antiderivative. That's your fundamental theorem of calculus. Of course, there are restrictions on the function and the interval and so forth. Okay? And so Green's theorem relates a line integral to an integral over a 2-dimensional region, okay, in the same way that your integral of a function in one variable, okay, relates an interval to an area, okay? So, you know, interval to an area, that's a 1-dimensional to 2-dimensional, right? In the area being the area of the, under the curve, which is defined by the antiderivative, okay? Okay, so you can go up 1 dimension. And yeah, it's a little bit of a hand-waving explanation, we could formalize it. But we go up 1 dimension, so a line integral is 1-dimensional, we can go to a surface integral now. Stokes' theorem kind of generalizes Green's theorem. Okay, one form of Green's theorem, okay?
Green's theorem is for 2 dimensions, right?
Yeah. Yeah, it's for a boundary of a region in the plane. Okay, you kind of blow that up well into a surface, you kind of deform the thing into a surface, and you get a version of Stokes' theorem, okay? And that's, of course, when the line integral is the integral of the curl, okay? Because it's like the circulation. Actually, it isn't. Yeah, I mean, you get Stokes' theorem if you use the curl version, the circulation version of Green's theorem. Okay? Anyhow, you know, I think I just said something that wasn't quite right, but I'm not going to worry about it. Just getting the general concept. Or you could go from a surface integral, which is an integral over a 2-dimensional region, to volume integral, which is a 3-dimensional region. Okay? So you kind of have something like the integral over a closed curve of something equals a double integral over an enclosed region, right? The region enclosed by the curve, okay? Okay, well, this integral here, in the case of the Stokes theorem, actually, the book uses a dr. F dot dr over this curve, okay, should be equal to the integral of the curl of F I'll do a dot n d big S, where this is your surface area.
What's the difference between big S and little s? Like,
I just said, this is surface area.
so
This is your surface area integral, okay? And it actually, okay, let's just call that, avoid the confusion, dA, because that works, where A is in the area increment, okay? And I got rid of the S here because of that possible ambiguity, okay? This would be a little s, that'd be a big S. So that your n dot dA is vector ds. N being your normal vector, okay? Okay, well, anyhow, that's your generalization, that's Stokes' theorem. Okay, and the divergence theorem says, okay, double integral over closed region over a surface, okay? Of let's say F dot n dA, the flux through the surface. So this is flux through the surface, and this would be over, I'm going to use S for the surface.
I think that's what the book uses.
Yeah. Different texts will use different notation, but that's more common. Okay? But we also have this with a vector, and that's not an uncommon notation. Okay, so anyhow, we have this. This is your flux through the surface. Okay? And that should be your triple integral over the entire region of divergence. Okay? And we could say this is maybe the total divergence within the region. Okay? Within the region, volume region. Okay? Now, that's not a full statement, there are restrictions and so forth, but that's the feel of it, and that's got most of it. And then if you understand the finer details, which you will in the process of doing a bunch of problems, you'll be able to distinguish these, okay? And I've been a little careless with little n's and big n's, there are conventions around that, but you gotta nail down the details, okay? So now we want to verify Stokes' theorem, that's this one. So we have to have a boundary and a region, an area, a surface, okay? Well, the surface is just the 5 faces of this cube that don't include the open one, right? And the boundary of that surface is what?
The top of the cube.
Top of the cube doesn't form a boundary for the surface. It forms a boundary maybe for the volume region. But in the first place, you have to have a curve, not a surface. Top of the cube is a surface.
So the 4 edges of the top?
Yeah, the square at the top, okay? In one sense or another, okay? And we haven't yet really nailed down the idea of orientability, but that's relevant to the direction in which you set up your Okay? Right now, we're just going to go counterclockwise. Okay? And of course, on some surfaces, you can't distinguish counterclockwise from clockwise, at least not easily. And those would be like non-orientable surfaces, okay? In which case, you got to be careful what you do, okay? So yeah, we'll get into that. Okay, well, I want to verify Stokes' theorem for this, okay? So, it's a square bounding the top, and it's counterclockwise, right? And then your region R I'm going to change my notation. Okay, it's a surface, right? So make it look like a surface. Surface is it's the 5 faces of the open cube. Well, when you do a line integral around this square, you have 4 edges. You have to integrate for each one. It's no big deal, okay? Although it may be a little tedious. And you have 5 faces of the open cube. You're going to have an integral for each face. So I'm not going to do all the integrals, but we're going to set a couple of them up and just kind of see what patterns we expect from the others. Okay? So I guess I'll observe one thing here, that, for example, on any face in the face in the XZ plane, y is 0, right? And on a face in the YZ plane, x is 0, and so forth. Okay? So that might help a little bit. Maybe if I'd have mixed up some of these coordinates, it would have helped even more, but we'll stick with what I've got here. It's going to be fairly simple. Things are going to simplify to a good extent. And on any edge, because there are 2 edges of this thing, like in the YZ plane, okay, well, x is 0 on both of those edges, right? And your normal is in the x direction. So when you do the f, well, we've got to go to the curl. We've got to get the curl before we can do much with it. But we have those kinds of things that can maybe help simplify just the tedious details. And they're not all that tedious because the integrals are all pretty simple. Okay?